there are a couple of ways to talk about what has to be true or what always happens when objects interact with other objects. Now, when we say objects here, we have to talk about, or we have to specify what we mean. Um, well, because one way to talk about objects is as one way to talk about objects is as point masses. That sounds strange. You can talk about objects as point masses. You can also talk about objects as, well, non-point masses, objects with shape and size, right? And depending on the context in which you look at these objects, there are some different intricacies that happen, but, well, the same sort of principle can be applied, all right? If we start with the point mass thing, well, when two objects interact, now, when we say interact, what do we mean? When we say interact, we mean by definition, apply force to each other. So let's take the simplest case we can, where two objects apply forces to each other. Two objects interact. Well, no matter what, here's a case. One object is coming at another one, and the other one's coming at that one. There's one case. Here's a second case. One object bumps into a stationary one. Here's a third one. Two objects start together and push off of each other and do that. But yeah, here's a different case where this is a big one and that's a small one. Or this is a big one and that's a small, but point mass, not big, just massive, right? More massive. Oh wait, what about this case where like there's one object is moving this way and another object moves that way? Ooh, yeah, okay, sure. Well, in any of these cases, right, if we say this is object 1 and this is object 2, well, what has to be true, I don't know if by definition is the right way to say it, but the forces that those two objects exert on each other have to be equal and opposite. By F1, I'm saying, let's say here's object 1 moving with a speed v1 initial that way, and here's object 2, moving, let's say this way, v2 initial. During the time interval over which they exert forces on each other, well, there will be a force that I would call F2 exerted on object 1. And there would be an equal and opposite force that I'll call F1 exerted on mass 2, right? Mass 2 exerts force 2. Mass 1 exerts force 1. And regardless of anything about these objects, regardless of anything about their speeds or how massive they are or what color they are or what street they live on, and regardless of anything, the forces they apply to each other have to be equal and opposite. All right? These two forces are part of a force, well, are the two components of a force pair. Okay? And remember, I said these forces, or at least there's an average force, right? Because let's say these two objects, just start to interact, and so maybe in the beginning there's a force on 1, and here's 2. In the beginning there's a force that is small and small, and then they get closer together perhaps, and they're smushing more, and the force gets bigger and bigger, and then later the force gets smaller and smaller again, blah, blah, blah. So there's some average force that these objects exert on each other. And that average force has to be equal and opposite, right? And when we say that average force, we're saying the force changes over time. And so F1 is applied for some interval of time I'll call F or delta T1, and F2 is applied for some amount of time delta T2, and those times have to be the same. It's impossible for those two forces to be applied for different amounts of time, which says we can take, well, each of these two quantities and multiply them by an equivalent quantity and get this. We get F1 delta T1 is negative F2 delta T2. All right? And we know that F can be expressed as MA, M1 A1 delta T1 is negative M2 A2 delta T2. Now I am saying that this is a net force, right? There's an unbalanced net force here, right? A net force, and really an average net force. And then A delta T. Well, acceleration, remember, delta V over T. So A delta T is delta V. So this says, well, that M1 delta V1 is M2 delta V2. Negative. And this, well, we have said is by definition change in momentum or impulse. All right. So it says, you know, our example here says that when two point masses interact, regardless of anything, regardless of directions they are moving, speeds they are moving at, relative masses, the forces they apply to each other are equal and opposite. Those forces are applied for the same amount of time, and therefore the two objects experience equal and opposite impulses. Which means, like, you know, and let's take this case right here. We'll say object 1 here is moving this way. Well, it might lose some momentum when it bumps into object 2, or while it interacts with object 2. Well, if it loses some momentum, and there must be equal and opposite changes, then mass 2 must gain some momentum. And it must gain the same amount of momentum. All right? And so if these impulses are equal and opposite, I'll say that during a two-body interaction, momentum is conserved. Please notice, there has been no mention whatsoever about energy or kinetic energy, because that has, well, cannot be related necessarily or directly to the product of force and time. That would be like more about like the product of force and distance. Okay? But anyway, yeah, during two-body interactions, momentum is conserved. Now, what we do have to say is in all directions, which is to say that momentum is a vector, because force is a vector, and delta V is a vector, right? So we've looked at situations where, let's say we have an object with a momentum like this. Here's object 1. And let's say it's about to collide with an object that has a momentum like that. And let's say those two objects hit and stick together. Well, when they do that, we're going to end up with a combined system that has, well, a momentum that's equal to the total momentum that the system had before, because we're saying, right, that net initial momentum is the same as net final momentum. Remember, momentum is a vector. So these two momentum vectors, here's P1 initial-ish, here's P2 initial-ish. Gives you some net initial momentum that looks like that. And by definition, that says, well, if that's the net initial momentum, then it's also the net final momentum. All right, it can be difficult to do a problem like this without drawing things to scale. So the process that we would go through if we ever wanted to look at a situation where there was more than one dimension involved is we would have to do something like this. We would say P1 initial X, P1 initial Y. Let me do this. P2 initial. So here's P2 initial X, and here's P2 initial Y. All right, what we would have to do if we were to solve this problem is we would say, momentum is conserved in all directions. So let's look at these two individual directions separately and say the initial X momentum and the final X momentum have to be the same. The initial Y momentum and the final Y momentum have to be the same. And if you look closely at the two vectors and their general components, well, it does work out that this is about, right, P1 initial X plus P2 initial X. And this small downward component is really P1 initial X, or Y, plus P1, P2 initial Y. But really, it's the two vectors added up. One of them happens to point down. And the one that points down, right, is bigger than the one that points up, so the net momentum down, it has to be downward. And of course, we could say something like the net final momentum is the sum of the squares of the two components. And the same thing would be true if these things didn't hit and stick together, right? We just have to look at the components of the first object and the second object initially, and the first object and the second object afterwards, because it might not be that the two things stick together. They might each have their own final X component and final Y component. Okay? Notice, there is nothing here about kinetic energy being conserved. In the vast majority of real interactions between objects, kinetic energy is not conserved, because objects do this. They whack into each other and produce sound. Or they whack into each other and objects are deformed, and that creates thermal energy. Or some of the kinetic energy is transformed into thermal energy. Okay? Okay. Now, going back a minute here, we've spent some time talking about when point masses interact, right? And what I should say is, in the simplest sorts of situations, or the most kind of bread and butter solution ends up looking something like, for 1D, one-dimensional stuff, which is pretty straightforward stuff. You end up with this thing M1V initial plus M2V2 and M1V1. Yeah, M1V1 initial plus M2V2 initial equals M1V1 final plus M2 V2 final, right? And you got to be careful about directions, things going right or left or up or down, right? And then sometimes for the 2D stuff, we have to turn this, we have to do one for X and one for Y separately. That's what we just kind of talked about in this second slide here. Okay? But that's the bread and butter, you know, procedurally, is that you probably end up with something like that. But knowing why that is, knowing that forces are equal and opposite and time intervals are the same thing, so therefore the product of F and delta T is the same, and therefore that means the impulses that each part of the system experiences are equal and opposite, and that means that by definition momentum has to be conserved. Linear momentum has to be conserved. For a system of point masses. It doesn't have to just be two objects. It can be n number of objects. Okay? Now, when we don't deal with simple point masses, when we deal with things like, well, that have shape, you know, if an object that looks like that, let's say, is just sitting there, and this is really like, oh man, I'm asking for trouble. But let's say this instead. Let's say that we have like some sort of base like this, with a little pin. It looks like a candle. It's not a candle. You know, this is a meter stick. Let's say that's supported by this what do you call it? Some sort of pin, some sort of pivot, right? And this is a thing with shape and size. So we get a top view of this thing, right? Top view like this. Well, and we have an object that we shoot at it like this. No, I don't like this example. Let's do a different one. Let's talk about, yeah, sure. You have a spinning disc, or you have a disc that somebody sets a spin in. It's spinning along here with an angular velocity omega. Now that's not the direction of its angular velocity. Don't worry about that for now, my folks. Its angular velocity actually points this way. Don't worry about it. And let's say this thing is a spinning, and what we do is we take an object up here and we let it drop onto that tray. All right, from a top view, here's the rotating disc. Let's say it's spinning this way, and maybe the other way, huh? No? Yeah, it's spinning this way. I got to do a better circle because it's a curse that I have. Let's see. All right. Just leave alone. All right, so this thing's spinning like this, and well, when the object is dropped onto this spinning disc, it spins, rotates about an axis located at its center. Well, not only is there a force applied to this disc, there's a force applied here. And that force, well, let's see. The mass itself that we dropped onto the table feels a force, well, this way. And it's a frictional force. Agreed? And that means that there's an equal and opposite frictional force. This is, how about on ball by plate? This is on plate by ball, or disc, I should have called it instead of plate, but you get it. Right, and guess what? These two forces are equal and opposite. Now, this really does happen over here, right? It happens right there. And notice that these forces obviously are applied at the same distance r from the axis of rotation, which says that for this system, well, there are not just two forces that are applied to each object. There are, but where those forces are applied is important, okay? And what we can say here is that F, let's see, yeah, F, let's say, let's just call it 1. We'll call one of them 1 and the other one 2. F1 is the same as F2, equal and opposite. And the r's are the same. So we can say that F1r is negative F2r. And the important thing here, yeah, sure, is that each object experiences an equal and opposite force, but we say our net force, right? Net force, net force, net average force, sure. But we're also concerned about where those forces are applied, and they are applied at the same distance from some axis of rotation, which means that these two objects, these two parts of a system, experience the same net torque. Well, it's the same, but it's equal and opposite. Okay? Now, net torque, let's see. Net torque. Oh yeah, torque is I alpha, right? So we can say that I1 alpha 1 is negative I2 alpha 2. Now, for the rusty among us, I equals moment of inertia, or rotational inertia. Alpha equals angular acceleration. And angular acceleration, let's see, angular acceleration, that's rate of change of angular velocity. So we can say, let's see, that I1 delta omega 1 over T1 is negative I2 delta omega 2 over T2. And guess what? The times that each of these forces are applied for, or that each torque is experienced by each part of the system, those times are the same amount of time. And this says, well, I omega 1, or sorry, I delta omega 1 how about this? It says that two objects experience equal and opposite products of I and delta omega. Well, that's sort of like saying, remember from the last slide, M delta V? We wrote it as M1 delta V1. It's analogous to saying this, right? And this one said for us that, well, that delta P1 is negative delta P2, and that linear momentum is conserved. Because each part of the system experiences an equal and opposite change in linear momentum. Therefore, there's a constant amount of linear momentum. Well, in this case, notice, instead of regular old mass and linear velocity, we have the rotational analog of mass and rotational velocity. And so I and omega, the product of I and omega, is what we call angular velocity. And this says that when two objects or systems interact, that one part of the system experiences some change in angular momentum, and the other part of the system experiences an equal change in angular momentum, except in the opposite direction, which is to say that during multi-object interactions where the parts of the system are not just point masses, but they're objects with shape and size, that angular momentum is conserved. Okay? So, if we did, there's a case like this where we can look at, here's one object of mass m and speed v. Here's another object of the same mass. How about they hit and stick together, and so then you have an object of mass 2m. Well, we would say here, right, m1 v1 initial plus m2 v2 initial is m1 plus m2 moving at some final velocity. And this is really just mv, because this goes, and this is 2m v final. And look, the masses go, and in this case, right, a nice simple case, we get v final is half the original v, right? Sure. Well, as a rotational analog to that, let's take one disk, and it's rotating at some angular velocity omega, but we take another disk that's stationary, but it has the same exact dimensions. It has the same mass, it has the same radius, but it's not spinning, but we drop this one down onto that one. And they hit and they stick together. Well, notice up here, what we actually said, what we were actually doing was saying that you take the linear momentum of the first one plus the linear momentum of the second one initially, and that gives you the 1 final plus 2 final. The sum of the initial momentums linearly is the sum of the final momentums. Well, in this case, we can't say linear stuff. We have to say, because these objects' centers of mass aren't moving, but they're rotating, or this one is at least. So what we say here is L1 initial plus L2 initial equals L1 final plus L2 final. And instead of P is mv, we say L is, well, you know what? This one just goes away. If this is 1, and this is 2, and this one is not rotating, see ya. Well, let's see, L is I omega. Well, if these two things stick together, then I would say I system, like we did M system here, times omega phi. All right, so what's rotational inertia of a disk? Well, it happens to be 1/2 mr squared, omega. We just called this omega, right? Equals, well, the system's now just a disk with more mass. Yeah? Okay, see ya. All right, bye. Oh, look. I don't need you either. Ah, well, looky. Omega final is divide omega over 2. Sure. Okay. Those are the analogies we can draw between what happens to point masses when they interact and what happens to one example of different kinds of objects that are capable of rotating when they interact. The tricky part about this stuff, about doing the angular stuff, is you could have, well, things that can rotate. We got disks, we got rods, about their center and about their end. You got the spheres there. You got the hoops. You got your point masses that move in a circles, right? So the question is, what do you end up using? I mean, this still has to be true, no matter what kind of objects are interacting, if they're objects that can rotate. But the question is, what do you use for I? All right, but we'll give you that. There's nice common tables of common, what do you call them? Common rotational inertias or moments of inertia. Okay, but in terms of concept, the overarching theme here is, well, the overarching theme is that when objects interact, momentum is conserved. And it's either linear or angular. Okay? Hope this helps. The thing that I just realized I didn't say that I should is a little caveat. Sometimes, but rarely, very, very rarely. All right. For the rotational stuff, it's almost never that you'd have the same kinetic energy before and after, because it would mean that things didn't or couldn't come in contact. All right. But we've seen cases where, like, oh, what if we had like a positive charge approach another positive charge? Well, they could interact without touching each other, and in that case, kinetic energy would be conserved. All right, but most of the time not. Most of the time, one of the questions is to find how much kinetic energy is lost. I wish I hadn't added that part. It was, oh well. Kinetic energy, sometimes, very rarely. All right, but always, 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 momentum is conserved when objects interact. There, forget I added that last minute. Bye. Darn.